Today, we're going to demystify a really crucial but honestly often hidden layer of our modern world, and that is grounding technology. I mean, think about it. Every single piece of electrical infrastructure we rely on absolutely has to be protected from massive, catastrophic electrical surges like lightning strikes. But the way we've been doing it for decades, well, that is fundamentally changing. Today, we're exploring a revolutionary leap in critical infrastructure protection. We are talking about a true paradigm shift in earthing technology and transient surge absorption, and it's all driven by something called the Monolithic Nano-Chemical Earth Mold. Okay, let's dive right into this. Here is a quick look at our agenda for today. First, we'll cover traditional grounding, then move on to the paradigm shift. Next, we'll look at how nanomolds work, followed by energy storage, testing and validation, and finally, protecting infrastructure.
Traditional grounding and its inherent flaws and vulnerabilities. All right, so think of traditional grounding kind of like a simple drain pipe in your backyard. It relies entirely on having perfect, highly conductive soil and really deep ground penetration to essentially drain a massive transient surge away from your equipment. But what happens if the soil is rocky or dry or simply can't take that much electricity all at once? Well, the drain backs up. The surge has literally nowhere to go, and your highly sensitive, incredibly expensive equipment just gets fried. But transient surge absorption completely flips this dynamic. It internally absorbs the surge, acting totally independently of how bad or uncooperative the soil conditions around it might be. The paradigm shift, internal absorption. The old way of doing things was basically a copper rod desperately trying to push all that violent energy outward into the dirt. But the monolithic nano-chemical mold functions entirely differently, acting simultaneously as an earthing medium and an internal surge absorber. The absolute game changer here is that low earth impedance, which just means perfectly conductive soil, is no longer strictly required. Instead of just being a passive pipe, this mold acts like a massive sponge, violently pulling in the surge and absorbing it internally before it can bounce back and cause any damage. Let's get into the weeds of how nanomolds actually work. The atomic physics mechanics. It all starts with the physical architecture of the material itself, which is this incredibly dense molecular matrix. The core structural polymers, so things like polyurethane, epoxy, polystyrene, and polyacrylic, they step up to create a robust physical framework. But the real magic happens with the active agents embedded right inside of it: nanocarbon, nanophosphate, and some highly specialized sulfonates and stearates. These active agents are exactly what transform the structural block into a highly reactive, energy-absorbing powerhouse. So the first mechanism at play here is something known as the choke effect. Now, if you remember your high school physics classes, Faraday's law might ring a bell. In simple terms, this mold basically operates as a massive inductor. When a sudden spike of electricity hits the system, say a direct lightning strike, the high inductance of the mold generates a reverse voltage that actively fights back. It vigorously opposes the sudden transient changes. It acts as a physical buffer that literally wrestles the electrical spike, forcing it to slow right down. Without the nanomold, a terrifying, sharp, violent spike in current instantly destroys whatever connected equipment is in its path. But with the nanomold in place, the rise time is drastically slowed down and the peak of the current is heavily attenuated, which basically means it's flattened out. By stretching all that energy out over time instead of letting it hit all at once, your connected equipment is completely protected. Now, once that surge is actually slowed down, we hit mechanism 2. Non-linear charge redistribution. That active nanocarbon we talked about earlier, it actually forms a graphene-based conductive layer, and graphene is absolutely famous for its incredible electron mobility. When surge electrons enter this hexagonal lattice, they don't just travel in a straight line. Because of electrostatic repulsion, they instantly scatter and redistribute outward throughout the whole structure. This is huge, guys, because energy is progressively attenuated rather than discharging at a single focal point, which completely eliminates the localized heating and melting that routinely destroys traditional grounding rods. Energy storage and its unprecedented capacity. 5 billion coulombs. Just let that staggering amount of electrical charge capacity sink in for a second. Let's actually break down how we arrive at a number that massive. A typical heavy infrastructure nanomold weighs in at about 42 kilograms and contains roughly 16 kilograms of active carbon. Because each carbon atom can theoretically donate or accept up to 4 electrons, we can apply Avogadro's multiplier, which is just a way to calculate the number of atoms in a given mass. When you multiply the sheer volume of carbon atoms in 16 kilograms by their electron capacity, you hit a theoretical maximum capacity of 5 billion coulombs. This vastly exceeds any conventional earthing media in existence. It gives us an immense, almost unfathomable buffer against extreme transient surges. Testing and validation, the real-world data. Contact resistance testing data straight from the University of Maratwa reveals a very clear winner. Look, in electrical grounding, you obviously want the lowest resistance possible, right? Well, the nano-chemical rod demonstrably outperforms all the conventional metals. It ranks number 1 with a resistance of just 1.457 kiloohms, beating out iron, solid copper, and copper-cladded rods by a really significant margin. So the science works in the lab, and it absolutely works in the field. But the current carrying capacity per unit is where things get truly jaw-dropping. Let's say you need to protect a massive facility from a 625 kiloamp surge. If you use standard 16mm solid copper rods, you would literally need an array of 15 separate electrodes dug into the ground just to handle that load. But a single 5x5mm nano-chemical mold possesses an unparalleled current carrying capacity of 625 kiloamps entirely by itself. Literally one unit doing the work of 15 solid copper rods. It's wild. So what does that actually mean in practical reality? Well, it gives engineers a massive geometric advantage. Normally, you'd have a conventional grounding array, a sprawling, complex, incredibly expensive network of rods and copper wiring that requires a huge real estate footprint and perfectly conductive soil. But with this tech, a single monolithic module provides a 30x replacement advantage. By swapping out those massive arrays, installations can save up to 180 meters of additional bonding conductor, saving immense amounts of copper, labor, and massive excavation costs. Protecting infrastructure, scalability, and deployment. The beautiful thing is, this technology scales incredibly well. For residential and light commercial applications, a domestic monolithic nano-mold handles a highly respectable 50 kiloamp surge, and for heavy infrastructure and high-risk zones, the 42 kilo module handles up to 600 kiloamps. And crucially, because it's chemical and internal, it maintains consistent earth resistance over time. It doesn't matter if you're in a wet spring or a massive seasonal drought, it performs identically. The absolutely crucial point here is that this isn't just some theoretical idea on a whiteboard. With a highly proven track record in mitigating lightning-induced failures, this internationally patented technology is already offering highly cost-effective upgrades to infrastructure resilience. In fact, major institutions like the Public Utilities Commission and the Ceylon Electricity Board are currently considering it to protect their critical transformer installations. It is quite literally ready for next-generation pilot deployments.
So, as we look to the future, we really have to ask ourselves, with transient surges and weather events growing more and more extreme by the year, are our current soil-dependent infrastructure grids truly ready? Or is the shift away from simply trying to drain electricity into the earth and moving toward this new paradigm of internal surge absorption now an absolute necessity? It's a fascinating challenge for forward-thinking engineers and planners everywhere. Thank you so much for joining me to explore this incredibly vital leap in technology. Keep questioning, keep learning,